Hey there, in this video, we're going to look at what happens when we have a system of equations that isn't quite set up for elimination, but we still want to use elimination. So we can actually multiply or divide both sides of an equation. So remember, it has to be both sides of the equation before we actually use the elimination process. I also want to remind you that we have to do it to both sides of the equation. So I know I already said that once, but it's super important that you remember that we do that on both sides of the equation. So let's take a look at number 1. X plus 9 equals 2y, 3y minus 2x equals 5. Notice that we have our x's on the same side of the equal sign, and our equal signs are lined up, but our constants are on different sides and our y terms are on different sides of the equal signs. So I'm going to go ahead and start with that first equation. I'm going to get my x's and my y's on the left side and my constant on the right. You don't have to do it that way, but I would suggest putting your x's and your y's together on one side and your constants on the other. So x plus 9 equals 2y. If I want to move the 2y to the left side, I'm going to subtract 2y from both sides. It won't combine with anything on the left side, so I'm just going to write it over here. But that will cancel out that 2y that's on the right side and move it over. In the same step or in a different step, I'm going to subtract 9 from both sides. By subtracting 9 from both sides using that inverse operations, it cancels out the 9 over here, and it puts that negative 9 over here. So I now have x minus 2y on the left side equals negative 9 on the right side. So this is the equation I'm going to use as one of the two equations in my system of equations. Now, in the second equation, it is already written in a similar format to what I just got, but I'm going to switch just for efficiency purposes and lining it up easily. I'm going to swap the order of these two terms. Now, the negative does go with the 2x, so I'm going to have negative 2x plus 3y equals 5, and that's going to be my second equation in this system of equations. So if I write them one on top of the other, so negative 2x plus 3y equals 5, and x minus 2y equals negative 9, when I set those up, if I were to add down the columns right now, the x's would not cancel out because I have a negative 2 and a 1. The y's would not cancel out because I have a 3 and a negative 2. So notice that when they canceled out, like in the previous video, they had to be the same numbers but opposite signs so that when you add down those columns, you would end up with 0. Or if you didn't want to worry about getting opposite signs, you could do the exact same number, and then you would have to remember to subtract down each column instead of adding. So looking here, I'm going to go ahead and use the x's. So I'm going to work with this x column here, negative 2x and 1x. I want to get these to be the same number, but opposite signs so that when I add down those columns, they cancel out. And I'm picking negative 2 and 1 because I can actually just multiply this second equation by a number that will turn this 1 into a positive 2 so that when it's added with the negative 2 up here, I get 0. And in order to do that, I'm going to multiply by positive 2, and I have to do it on both sides. So I will do it to each term in this equation. And again, I picked the x's instead of the y's because 1 could be multiplied by a whole number to give me 2, and 2 plus negative 2 is 0. With the y's, negative 2 can't be multiplied by a whole number to turn into a negative 3 so that it can be added or subtracted with the 3y on the top here. So I would not suggest doing the y's here. I would suggest doing the x's. So let me show you what we get when we do that. So the top equation is going to remain negative 2x plus 3y equals 5. The bottom equation is going to now be 2x minus 4y equals negative 18. And again, I just distributed that 2 to each term in that second equation. Now that I've done that, I just go ahead and add down the columns, and I add my x's, I add my y's, and I add my constants. So negative 2x plus x is 0. Those go away. Then we have 3y plus negative 4y, which is the same as 3y minus 4y, which will be negative y equals 5 plus negative 18 or 5 minus 18. When you do that, you get negative 13. Now, y is not quite isolated yet. I need to divide both sides by negative 1 so that that negative 1 in front of the y cancels out, and we just have y equals 13. Once I have y equals 13, I have one variable. I go back to my original equations. It does not matter which equation you plug into, but you pick one of those two equations and you plug in the 13 for y, and then you solve for x. So I'm just going to do that first equation, x plus 9 equals 2y. So when I do that, I'm going to plug in x plus 9 equals 2 times 13. So I plugged in that y equals 13 for the y in that equation. At that point, I just solved. So x plus 9 equals 2 times 13 is 26. And then I subtract 9 from both sides. And when I do that, I get x equals 17. So my x coordinate is 17 and my y coordinate is 13, and that is the ordered pair. That is a solution to this system. And again, to check yourself, you can plug in 17, 13 into both equations and see that they will both check out to be this equals this in a true statement. Now, the second example I have here, 3x minus 2y equals 2, and 5x minus 5y equals 10. If you look at this, it is already lined up. Your x's are lined up, your y's are lined up, equal signs and constants. So the lineup is fine. However, you'll notice if I look at my x's, 3 is not going to be multiplied by a whole number to give you 5, and 5 can't be multiplied by a whole number to give you 3. If I look at my y's, negative 2y can't be multiplied by a whole number to give you 5, and negative 5 can't be multiplied by a whole number to give you 2. However, we can still use elimination on this problem. So to do that, we are going to have to multiply both equations by a whole number so that we can either turn the x's into the same coefficient or the y's into the same coefficient. It does not matter which one you do. For this one, I am going to go ahead and look at the y's. Again, you could absolutely do the x's, but I'm going to go ahead and look at the y's this time, just since I showed you with the x's on the last one. So here, 3x minus 2y equals 2, and 5x minus 5y equals 10. I'm going to look at the y's, and I want to turn those into the same number. So with this, you are essentially looking for the least common multiple between those two numbers. And if you think about 2 and 5, if you start with the bigger number and ignoring the sign, the negative signs, but start with the bigger number 5. So obviously 2 can't be multiplied by a whole number to give you 5. If I go to the next number divisible by 5, that's going to be 10. 10 can be divided by 2, which means I can multiply this 2y by something to turn it into a 10y or negative 10y. So I'm going to use 10 as the ideal number I'm aiming for in my rewriting of these equations. So what I'm going to do is I'm going to go ahead and multiply the top equation by a number that is going to turn this y term into 10y or negative 10y, however you want to look at it. I'm just going to go ahead and multiply by 5. So this will turn this into a negative 10y. Okay, we will have to distribute it to each of the terms, but right now I just want to make sure that the y's cancel out. So I'm just going to focus on the y's to start. Once I multiply that by 5, I also want to go ahead and multiply the second equation by a different number to turn this negative 5y into a positive 10y. And we want it to be positive 10y because I have a negative 10y up here, and those will add to be 0. So in order to do that, negative 5y, I can multiply that by negative 2 so that this y term turns into a positive 10y. So I will, here in a second, multiply that negative 2 by each term in that equation. So looking at the first equation, if I distribute the 5 times each term, 5 times 3x is 15x. 5 times negative 2y is negative 10y. And 2 times 5 is 10. So 15x minus 10y equals 10. For the second equation, I distribute that negative 2. So what I get, negative 10x plus 10y equals negative 20. Now at this point, I can go ahead and add down each of these columns because I have done the work to turn this into two equations where when I add down the columns, the y's are going to cancel out to be 0. So 15x plus negative 10x, I get 5x equals 10 plus negative 20, which is negative 10. And now I have an equation with one variable that I can easily solve to get that x by itself. And to do that, I just use my inverse operations. I divide both sides by 5, and I get x equals negative 2. Once I have my first variable, which in this case is x, then I go back to my original equations and I plug that negative 2 into either one of these two equations. So I'm going to go ahead and do it in the first one, 3x minus 2y equals 2. And when I do that, I have 3 times negative 2 minus 2y equals 2. 3 times negative 2 is negative 6 minus 2y equals 2. And then I go ahead and I add 6 to both sides. When I do that, I get negative 2y equals 8. And then I can go ahead and divide both sides by negative 2. And when I do that, I get y equals negative 4. So negative 2 comma negative 4 is the ordered pair that represents the solution to this system of equations. So as a quick reminder, elimination steps are the same even if it's not already set up for elimination. The only difference in the pre-work essentially to do elimination would be that you may have to multiply or divide both or one of the equations if necessary, so that when you end up with something like 3x and negative 3x, when you add down those columns, they cancel out one of the two variables, whether it's the x's or it could have been the y's. Maybe you had a 5y and a negative 5y. When you add down those columns, they cancel out. So that's the goal of elimination. So again, you may have to multiply or divide one or both of the equations in order to get them to eliminate. Again, just a quick reminder, you can always check your answers by plugging in whatever your x and your y terms or y values are from your ordered pair solution into both equations from the original problem. And if you do that and you end up with something like 7 equals 7 or 0 equals 0 or negative 9 equals negative 9 or something like that, a true statement, then it is a solution as long as it works in both equations.